Okay, so and this is kind of like an exercise session as well. Okay. So now let's do our x to x hat, the derivative to IP hat trick, right? So if you have a d-dimensional convection, okay, equation or advection equation, so this is just translation null mode, then we see a derivative, it becomes IP hat. But actually in this case we see that it's already a Schrodinger's form, right? And this operation actually is something that is very well known in quantum optics, and it's just it's something called a displacement operator, right? And kind of makes sense because you're displacing the state. And this is something that's very easily done in quantum optical systems, and we actually have an experiment running right now doing that. Yeah. So in general, simulation of PDEs do require entangling operations. But here we see actually, unless the initial state is complicated, we actually don't need, this. And you also go beyond Gaussian operations. So anyone who's heard of the term Gaussian operations before? Yeah, okay. So what it means in the context of the Hamiltonians is anything Gaussian is where, if it's a function of x hat or p hat, it's up to quadratic in x hat and p hat. Okay, so, and this is what's called like Gaussian, and this is something that is, easy on quantum optical systems. Okay, so this is something that is really feasible on existing systems already. But anything beyond quadratic, this is seen actually what's called non-Gaussian, right? And it's something that is much more difficult on optical systems, but then is more feasible on other kinds of platforms, okay, like superconducting circuits and so on. Right, and then I think I had a question yesterday. Maybe someone asked me about how do you go backwards, right? Someone gives you a Hamiltonian, right? How do you find the corresponding? So this is one example. Okay, so if you have a quantum optomechanical system, I don't know if you guys heard about these. So think about mechanical systems with a spring, okay? But now imagine that you can quantize, okay? These degrees of freedom, okay? So these are quantum optomechanical systems. And actually in the lab next door, like in the university next door to us, okay, we visited them, they have quantum optomechanical systems, and they gave us part of their Hamiltonians. They haven't set up the actual experiment yet, but this is the Hamiltonian. And then if you go backwards, you see that, it naturally, it corresponds to a Schrodinger-like equation, but now with a complex potential term and also a translation term. Yeah, okay. But you can use these slides also just kind of exercise on how to, use this, okay, because it's really very easy to use, okay. And here we have just, general, linear first order, okay, PDEs, okay. And if you use the trick, again, x goes to x hat, the derivative goes to, IP hat, then you can verify for yourself, okay, these operations. And actually, if you look at the form of A1 and A2, like what you notice, all of them are actually linear in p hat, okay. And what that means is that now if you take the tensor product with either hat, then at most, right, these Hamiltonians are Gaussian, right? Or these Hamiltonians being up to quadratic in x hat and p hat, then the whole operations are Gaussian, which means these are actually all feasible on quantum optical systems. Yeah, so if we try another one, okay, say Liouville equation, okay, now it's the same thing as the advection, but now the kind of the speed, okay, that you're looking at now, it's inhomogeneous, right? So, it can vary in space. So it just looks a little bit more complicated, right? But otherwise, it's all right. But now if you look at the terms, okay, everything here is actually very easily done on, in principle, on quantum optical mechanicals, on quantum optical systems. So if you look at the first one, it's A2. So now this is just kind of the identity or sums through the identity tensor product eta hat. So this is really just now the same thing as a translation operator, so which we know, is doable. Now on the second one, you see A1, well, we don't worry about the identity, okay, because it's just the identity. Now it's just this guy. Now this is x hat p hat plus p hat x hat. And this is something that is very well known in quantum optics called squeezing operation. Okay, I think some of you have, may have heard about that, but it's kind of like a textbook, example of, operations that can be done on, not just quantum optical systems, but actually, also on superconducting systems and so on. But it's, especially pronounced in quantum optical systems. So all these operations you see that correspond to, naturally occurring, PDEs. Yeah. And then it's something we can already see is feasible. Now, Black-Scholes equation, okay, so I can't tell you anything about the applications. I'm not a finance person. My students are doing projects, okay, on finance equations, so they can tell you a lot more about it. Yes, but this is just kind of like a fun example. So if we just do this raw, okay, so because there are transformations of the Black-Scholes equation to, right, a heat equation, okay, in which case, we can use what we learned about already. But here we see that if we, just use the raw one without any other transformations, then we're going to have operations like this, okay, x hat squared, p hat squared, and so on. And these operations, on at least quantum optical systems, we see that's very difficult because now we see it's more, right, than quadratic, okay? So this is an example that demonstrates that, however, if we translate it, into the heat equation, right, then it's going to have, a slightly different form, okay? So this actually tells you that even though we're all using Schrodingerisation, that actually we can do a lot of pre-processing, right, in terms of the PDE. That we can, depending on what kind of quantum mechanical systems that we have for implementation, we can actually put a lot more work into thinking about how to transform it, right, in such a way that is more implementable in one way versus another. And I'll have an example later of, what we do with the heat equation to make it, more implementable on devices now. Yes?
Do you know exactly what kind of equations, what's the name of equation on the Gaussian?
Yes, I do. We actually have a list in the paper, but you can already see, for example, all of these linear first order PDEs of these forms, where A is constant. I think when A is constant, B is constant. So here I actually compile all the Gaussian ones. You can check, like these ones are quadratic, and you can see where when J is constant or not, we're like linear in X, like versus like B. And it can be linear and it can also be quadratic as well. But you can try it yourself. It's super easy to do. And it's very possible I made typos in a lot of places. So you can point those out along the way. But you see, it's super easy to do because remember, just X goes to X hat, right? Derivative goes to IP hat, right? You get your A, and A is decomposed into A1 minus IA2, right? And that's it. And you get your Hamiltonian, right? That way. All right. Right, so, okay, and this is an example of the heat equation now where you have inhomogeneous diffusion coefficients, okay? So you see now this can be a little bit more complicated, okay? Depending on, how complicated diffusion inhomogeneity is. And here's a fun one, the Fokker-Planck equation. Actually, most of the important PDEs are like the Fokker-Planck. It's really just, in nature, you hardly have, third order or fourth order derivatives. Okay, there are equations, but, very few. So physics is essentially some combination of translation and diffusion. Okay, and Fokker-Planck's like that. It's just, translation with diffusion. And we know how to do translation, okay, with the advection equation. We know how to just do diffusion with the heat equation. So we should be able to do a combination, okay, of these. So as an example, for the Fokker-Planck equation, when we have linear drift and additive noise, and then if we look at the terms here, like you already see on the right-hand side here, this is a squeezing operation. This is something that we can do, right? But here you see we have the p squared tensor eta hat. Now this is very difficult to do on a quantum optical system, but it is something that, terms that people have, for example, on superconducting systems. So we have tried that for a while. But, it's a little bit difficult to control, right, on certain systems. So I'll show you the way that we can transform it so that it's even easier to do, okay? So it's not just that, in principle it's possible, but it's actually something that we have, that we're trying to do right now, actually. So I saw that Yue came in, right? So Yue, do you want to put up your hand, right, and say hi? So Yue is very much involved with all our, so we have 2 experimental collaborations right now. So we have experiments running on photonic and superconducting systems. So if you have any questions, right, about, more details about any of this, you can also catch Yue. And I asked him to also prepare slides, right? So, so in case any of you have questions, he will also have slides to show you. Okay, so now we looked at just, single, PDEs, but what about systems of linear PDEs? Okay, So, and of course, there are a lot of reasons why we would have systems of PDEs. I mean, first of all, when you just had them naturally, okay, as you would for a lot of applications. But also, and I'll give an example where, a single scalar PDE solution, it can sometimes be approximated by a system of PDEs, where that system is now more easy, right, to simulate than the original PDE. Okay, and we'll see this example, especially with the heat equation, because we see with the heat equation with also Fokker-Planck, we get this term like p squared tensor eta hat, which is not as easy on a lot of systems. So, but if we are able to approximate it by system of PDEs where the derivatives now lower order, right, then it's more easily simulable. Right, and if we're dealing with higher order time derivatives here, then we can also approximate this or transform this into a system of PDEs. And also when we have inhomogeneous PDEs, we see that we can also rewrite this as a system of linear PDEs. And again, inhomogeneous PDEs can arise either from just naturally, of course, as you would from source terms. Or as if we're in the discretise formalism and you want to input boundary conditions, inhomogeneous terms can also happen that way as well. And we'll see some examples of that. Okay, so here this is an example with a heat equation. We say, well, we can use Schrodingerisation directly, right, on this U tilde, right, heat equation. However, we see that, we have this p squared tensor eta hat term. And the fact that this is now non-Gaussian, right, with the, p squared, remember that p squared comes from the second derivative, okay? So somehow, if we want to lower, right, that power, then we should lower the order of the derivative. So then the idea is that, well, how do we lower the order of these derivatives? Okay, and one way to do it is actually to make it into a system, right, of PDEs, right? And we approximate the solution with the system. So this is now called a hyperbolic heat equation. I know people here, who do hyperbolic equations. And this is, you can see this as somehow like the fundamental equation that, would suggest why the heat equation would work, right? Or is physical. Because if we look at what the heat equation actually does, if you start off with something like a square wave initial condition, then immediately, kind of the next, epsilon time, immediately you're going to get an infinite tail, okay? Because kind of diffusion kind of happens with infinite speed. And we know that that's really not physical, okay? And, in nature, we don't actually lose information, okay? The fact that we feel like we lose information, it's kind of a thermodynamical aspect with this coarse graining. But at this level, but at this, this actually tells us that heat equation is not really fundamental in that sense. We shouldn't be losing information, okay, if we're keeping track of everything. So the hyperbolic heat equation is kind of an attempt at that to say, actually what's happening on the microscopic level, all you're doing is, having colliding particles, okay? Nothing's actually diffusing, okay? Or, you don't have information being lost, but you're just having particles colliding, but with a viscosity factor, okay? And then it kind of, when you zoom out, right, then it looks like things are diffusing. Okay, so we can think about this as, the fundamental, more fundamental than the heat equation that describes the heat equation. But the good thing, at least algorithmically for us, is that, the system of, the hyperbolic heat equation, sometimes called the Goldstein-Taylor equation, is that now it's first order derivatives. Okay, so when you have first order derivatives, that's only one p hat factor, okay, instead of p hat squared. Yeah, and then you can show, right, and this is just to show that, this system is a good approximation, right, that, at long enough times, okay, remember when you're zooming out of the system, okay, you're looking at this over a longer time period, then you can approximate U tilde, right, with, high precision, okay, like the larger your time, yeah. So now we can do Schrodingerisation, okay, now. So what we do is that now we have a system, right, of PDEs. We can define W, right, and W is a vector of, U and V, right? So in terms of, the qubit notation, right, how do we represent a vector? Now, each of the U and V, these are continuous variables, but because now U and V, because it's a system, now it's like infinite dimensional states embedded, right, inside, a two-dimensional, okay, state. You can think about it that way. So that's the same thing as 0 tensor product, okay, U of t, plus 1 tensor product V. Okay, let me see. Sorry, is there a laser pointer? Okay, let me see. Yeah. Oh. Never mind. Sorry, long. Yeah. So, but then, I mean, this is a very easy exercise, and you say, what is the equation in terms of W? Then we get this. But you see this kind of already, right? So we have, a factor here, okay, and a factor here, but everything here is still linear. Now, what does this guy remind you of in terms of things you've already seen in qubit-based quantum computing? Yeah, exactly. Excellent, right? So here this is, minus 1 over epsilon times, 0, 1, 1, 0, right, which is the sigma x, right, operator, okay? So we'll do that. Oh, thank you. Yeah. Thanks. Right, so now if you go through all of this, right, then we see that, we're placing sigma x, and here this is, 1, 1, okay? And now we have our A, right? And correspondingly, we have our A1 and then corresponding A2, okay? So very easy. And then we have our Hamiltonian. Now, so for those of you guys who do physics here, if you see terms like this, right, I mean, this is the James Cummings model, right? And this is something that is like textbook version of what people do in quantum optics. And what this is saying, right, I mean, the way to interpret this, so you saw that sigma x, what that does, it flips, right, from 0 to 1 and 1 to 0, okay? And what, p hat does, right, I mean, this is a continuous mode, right? So the interpretation of how people came up with this is that if you have a 0, 1 level of the atom, right, and then you have a light coming in, right, that's, whose, degree of freedom, right, it's given by this p hat. What this is inciting, right, your atom to go from 0 to 1, right, or falling back from 1 to 0, okay? Right, so, and this is, the most basic model of what's called, light-matter interaction, right? When you have, light, with just a two-level atom, okay? So, and sometimes, so this is called the electric dipole, and sometimes, this version with sigma z is called the magnetic dipole aspect. But the point of it is that now we've made this transformation, this kind of pre-processing, okay, of the heat equation to make this into our system. And then now we're seeing something that is, obviously that, people we know have, around. Even though the factors that might be hard to control, this is why it's taking us so long to complete the experiment. But this is, comparatively a lot easier than, having, millions of gates, right? And making sure each of them are accurate to the power, 10 to the minus, 7 or something. And I'll have some numbers for you later on, how many gates are actually required to what precision if we want to simulate this with qubits completely. If we want to discretise a PDE and then, go through the same procedure as you've seen, this week with linear algebra or other types of methods, right? Or block encoding and so on, okay? But so at least this is something, and at the moment we're following along these lines with our experimental collaboration. Again, you can ask him for more details, okay, about these. But you see, well, the heat equation is very fundamental because this is kind of the diffusion part, right, to all the PDEs, okay, that you can think of it. So we can also apply this to multidimensional, okay, PDEs. And in fact, this is kind of a good model for, Black-Scholes equations, right? So for finite applications, they have problems when you have multidimensional, Black-Scholes equations, okay? And, similarly for, Fokker-Planck equations, and this is the basic kind of circuit that you have for that. Now, so we have our, qmode and, our D qumodes to represent the original, system dimension. But we also have one qmode now ancilla for Schrodingerisation. But because we're doing this, our mapping to this hyperbolic, right, heat type of equation, then we also need to add in another qubit, remember, because now it's a system, okay? And then we have, a new Hamiltonian, right? We likewise, perform the measurement, okay, the post-selection, okay, onto the ancilla qubit. But here at the end, we're going to get a W state, right? The W state, remember, is the final state of U and V. But if we want to get out U, again, all we need to measure is, something like in 0 to get U, or if we measure in J to get V of J, okay, which is the derivative of U. Okay, so we just perform another post-selection. Find me. we perform another post-selection, okay, to get that. Okay, so this is an example of, so I just write down, okay, some terms, like, if we want to do 1D, 2D, 3D, or, D-dimensional problems, what is the size of the system? Okay, so if you want to do D-dimensional Fokker-Planck, for example, then you need one qubit or a qubit of D levels. Similarly, that's the same thing as log D, number of qubits, and then D plus 1 qmodes. Okay, so in terms of, that cost, it's, very small, right, in terms of D. And then the interesting Hamiltonian terms, interaction terms you will like, are things like, uj, j0, tensor, p hat j. And the interpretation for this one, right, before we looked at one dimension, then j is equal to 1. Okay, the interpretation is that what p is doing, so this light is doing, is interchanging 0 with j and j with 0. And so this is like if you have a j level atom, right, then the light is coming in, and the light that is coming in is then inducing, right, the state to go from 0 up to the jth level, right, and for that to fall back down. Okay, so then you can actually see, these type of interactions are very suitable when you have, atomic systems with, a lot of higher levels, especially want to go super high, right? So things like Rydberg type of atoms, you can get up to, 80 levels. Okay, so if you can control that well, just on a single atom, then you can, in principle, simulate, 80-dimensional, right, PDEs of these forms. Okay. All right. Oh, do we have any questions before we go on with that? No? Listen. So now how do we do higher order time derivatives? So here, the basic Schrodingerisation is just for, first order in time. But if you want to do, second order in time again, it's a very simple trick where we say, now we look at a system, right? But now we look at a system in terms of y, and y is now, defined, in terms of, the first derivative, okay, itself, okay? So then we have a system that's, du dt, and then, the second derivative, okay, of u, like with t, and then we solve, this system. Okay, so, and then I have an example with what we do with a simple wave equation, right, form. So with a simple wave equation, so we have now like the speed here, okay, also with, that's related to A. And now we see that Hamiltonian had this form like V2, okay, tensor product eta hat plus V1 tensor product identity. And we see A1, right, it's got this factor like P squared, okay, tensor now. And here, whenever you see these Paulis, it's actually suggesting it will be good to have what we call a hybrid system, like a hybrid qmode qubit system. And again, this is something like either light-matter interaction type of system or actually any continuous variable system. Because if you have, atoms, like, a lot of neutral atoms, right, or, ions, that are able to move around, then actually, their physical momentum itself, that itself is also a continuous variable you can exploit. Okay, so then you have to be, you can be creative, right, with what kind of platforms you use and have this, hybrid interaction between continuous variable and discrete variable. Okay, degrees of freedom. Okay, so these are a lot of the examples. Do we have any questions before we go on to unstable? No? Okay. All right, so everything that we've seen, right, so it's for stable systems because you may have noticed, the assumption that we have is that we want the original system, to be stable. All right. So how do we deal with, unstable systems? And in fact, it can also, be applied not just to backward in time, okay, dissipative linear PDEs like backward heat equations, but also to general inhomogeneous PDEs. Because if you have general inhomogeneous PDEs, as we saw before, we make it into a system. Right. So before, if you PD, the homogeneous part of your PD, if that was stable, when it becomes inhomogeneous and you put them into a larger system, then it can become in principle unstable, right? Because now you've kind of dilated the system, right? So you need to recalculate, its eigenvalues. So, then it has these applications. Right. So now if we have unstable modes, what it means is that now we have this general, right, linear PDE. And again, we can see how it would, do high orders in time. So I will just only talk about linear, okay, time from now. What happens if some of the eigenvalues of B2 here are negative? Okay, so we can, so I mentioned, applications for, inhomogeneous PDEs as well as backward PDEs. And also, as we'll see, iterative algorithms for linear algebra that we'll see tomorrow. Okay, so how do we deal with inhomogeneous PDEs? Well, again, also, so I said about, dilation, right? So if, F factor, this is, say a source term, then we define a new variable, okay, y, right? So, and y is a vector, like with u and f. Okay, that's, let me use my laser pointer, okay? So y is u and f, but we can write it in this way where, u tensor product 0 plus f tensor product 1. So now this is coupling between continuous variable now with a qubit setting. And if we, go through this, now we have a system now, new Hamiltonian, right, has this form, B2 tensor product eta hat plus B1 tensor product identity, where B1 now has this form where it's A1, okay, tensor product with, sigma Z, right? And then we have, sigma Y here, and B2, again, A2 tensor product sigma Z, and we have a sigma X term. All right. All right, so how do we deal with these negative eigenvalues? All right, so first of all, when we, dealt with only positive eigenvalues, right, where did that come in, actually, when we derive Schrodingerisation? So you might remember, like what I said at the beginning, that, when we apply the Ward phase transformation, the Ward phase transformation works when we have e to the power minus psi multiplied by u when psi is positive, okay? Which means that, and then we were able to extend to psi negative, okay? And the reason we're able to do that is that we see that in the heat equation in the phase space kind of picture, you can see it's really a translation where, the wave moves from, your right, okay, to your left, okay? So which means that we consider boundary condition at infinity, right, on the far right, and that will be 0 because e to the power minus psi goes to infinity, okay? So then w, okay, will be 0. But then it doesn't really affect the wave, okay, as you propagate to the left. So we don't need to worry about that. So then all we need to do is to capture, like, our wave from 0 to infinity. And this is why, to get back our u, this is equal to the integral of 0 to infinity, okay, of w. Or we can select any psi factor that is larger than 0. But the problem is that if now B2 has negative eigenvalues, then we see that, this translation, this B, like, you can think about the eigenvalues of B as the speed, okay, of different modes of that wave. Okay, so B2 is always positive, then it's always going like this, right? But if some of these are actually negative, it means there are some modes that are actually going backwards like this, okay? So if they're going backwards like this, it actually means it's going to disturb some of your solutions, okay? So therefore, when we do post-selection, we don't want to post-select, okay, all the parts that have been disturbed, okay? So then to deal with this, right, if we then we need to ask, okay, the wave that is causing the most disturbance, okay, we kind of want to cut that off, okay? So then you ask, well, what is the wave that causes the most disturbance? It's the one that moves in the other direction with the fastest speed, yeah? So, and the speed you can associate with the eigenvalue, okay? So now, like here, psi is the maximum, right, between the maximum eigenvalue, okay, the in the opposite direction, right? So then the distance that is traveled, right, will be the maximum speed multiplied by the propagation time t. Okay, so that is the part that you need to kind of cut off. So then to reproduce, okay, our original state, to reproduce our original state y, instead of now an integral, right, between 0 and infinity, then we actually cut it off at psi star, where psi star, again, is the region, right, that the worst, the fastest, negatively propagating wave has entered that area. Okay, so which means we can still do Schrodingerisation. It doesn't change the Hamiltonian, right? That part is still the same, but it's in the retrieval part where we're doing the integral. We need to select, right, the value of psi, right, where psi, psi is only 0. Okay, there are no waves propagating, okay, in the wrong direction. But if there are waves going in the wrong direction, then psi star can be large, depending on, again, the maximum absolute, value of the eigenvalue of B2. Yeah? So procedurally, algorithmically, nothing changes, right? Except when you're doing post-selection, right, of psi at the end, instead of asking, is this psi above 0? Then we keep the state. Okay, we'd ask, is psi above psi star? Okay. Yeah. Right, and then the probability of success, like here, it stays like this. Okay, but otherwise the circuit is the same. Okay, the Hamiltonian remains the same. Everything else the same. And here, the reason why the Hamiltonian doesn't need to change, like really, is because now, like Schrodinger's equation doesn't care if you're going forward or backward in time. Okay, so everything is still Hermitian, and everything is everything's still unitary, and everything's all good. Okay, so we have an example, right? So with the heat equation, for example, so recall, the foreign heat equation. Okay, it's like this. Now, if you apply the warp trace transformation, okay, now we get this with the minus sign. And if you remember, like here I said, this means W moves from the right to the left, okay, along the side direction. So only a boundary condition on the right is needed. But now if we do the backward equation, okay, so here, if we write the backward equation in terms of another variable, okay, V, okay, where this is, the backward propagating, okay, part, then we look at our new wave equation now with the initial condition now has a minus sign. Okay, so this is a backward propagating, okay, heat equation. So now if you use the warp phase transformation again, you see now instead of a minus p hat squared, right, we have a plus p hat squared. Okay, so which means that all the motion alongside is going from left to the right. Okay, so all the eigenvalues are actually negative. So this is like the worst, kind of propagating, okay, wave. So here, if we use our theorem, then the maximum eigenvalue, okay, is p squared max. Okay, but then you say, well, if we're doing it completely continuously, I mean, isn't that infinity? Like we can't do that, right? Then it doesn't quite work. But actually there are some possible strategies, okay, around that. Like first of all, like if your input data, right, is and it's Fourier transform, it has compact support. Okay, so then here your maximum momentum, you can think about, okay, your maximum momentum is bounded. Okay, so if it's bounded, then you just use the bounded maximum and choose p squared max t to be your psi star. Okay. And if your terminal condition is actually smooth in X, then the Fourier mode decays quite rapidly, and also you can also truncate your system that way as well. Or you can numerically discretize, okay, X, and also then discretize its derivative, and then you also have bounded, okay, maximum eigenvalue. Okay, so now I'll talk about the discretization, right, of the mode. Because I talk about discretization, what do I actually mean by that? Which of the qmodes can we discretize? Okay, so we can choose to discretize only the qmodes for the spatial degrees of freedom, okay, for the PDE, or we can choose only to discretize the ancilla, okay, qmodes, or we can choose to discretize all the qmodes, okay, and this again is dependent on what kind of platforms you want to choose and so on. Okay, so here you can have different numerical schemes, and so the idea is that to discretize the main qmodes, right, then you want to discretize A1 and A2 operators. Okay, so and here, for example, your X hat, right, there are diagonals, and if you want to say if this is a one-dimensional problem and you want to discretize your X dimension in n parts, okay, then the eigenvalues of X hat, right, would correspond, to the diagonal values, okay, of minus n on 2 all the way up to, n on 2 minus 1, okay? So if your X is in that domain, right, between minus n on 2 and n on 2, okay, minus 1. But now your P hat, this is an n by n matrix representation, but now this is now dependent on your particular numerical scheme. Like what do you mean by derivative? Okay, so there, you guys know very, very well, okay, that, all these numerical schemes are really different ways of representing the derivative, okay? So, and just as a note, that p squared, right, you think p squared is just, p hat times p hat, right? But when you discretize in matrix form, it doesn't correspond necessarily to the square of the previous matrix. So that's just something to be a little bit careful about, right? When you're discretizing this, don't look at p squared and just square the previous matrix. You have to, like, using a particular numerical scheme, looking at what you mean by second derivatives, okay? Or if you discretize the oscillar mode, then, eta hat is then the diagonal, okay, of minus m on 2 and m on 2. If you want to discretize eta, right, in terms of m. Now, m is not necessarily the same as n, okay, because we can see cases where we can make m actually really small, all right? So, whereas, with n, you have to make it big, okay, if you actually want good spatial resolution for the solution of your PDE. So as an example, and I got this off the paper with Chartier, okay, on Robin boundary conditions. So here when you have, so these are the different finite difference methods, okay, examples. Okay, and these things okay. So then you can see, okay, well, you can actually create, matrix operators, okay, dependent upon these numerical schemes. Okay, when you have U, okay, U1, U2, U3, remember as the column, like on the left. And if you want to do all these derivatives, then you can see it's really a matrix, right, applied to the column of U1, U2, U3, all the way up to UN. Okay. And you can derive what these matrices are. Now, and these are some examples of what happens when we do discretize, okay, our PDEs. So Chartier and another student that we have, Nikita, they're, what they do, right, like they have these explicit numerical, they have these explicit schemes where, dependent on different numerical schemes you use, and you put them on a real, qubit-based quantum device, okay, then you can estimate the actual cost in terms of actual numbers, okay, instead of just, looking at the asymptotic scalings of these, okay, these are the actual numbers. So suppose we want the solutions of the one-dimensional advection equation, right, to fidelity, say 0.9, as an example, then for different qubit numbers, right, these are the corresponding numbers of one qubit rotations and number of C-naughts, and, the requirement of single gate fidelities. Okay, so you might have seen in your, quantum error correction kind of lectures that we're not at these numbers. I mean, if you get really high, fidelity, single gate fidelity, then you can do error correction, so you don't need to worry about this. But this just gives you kind of a feeling of how far we are actually from doing this. So we can say, you can see these numbers are, are quite high, okay, these requirements. But actually using qmodes, we can already simulate, up to, a 200,000 dimensional probe. Okay, so this is just the contrast, at least for, these simpler, right, types of problems. Now for the one-dimensional hyperbolic heat equation, so we mentioned that we have experiments that we're running kind of right now that we hope to simulate these with superconducting systems. But if you want to simulate to 0.9 fidelity, again, with qubit-based systems using the discretization schemes, right, then these are kind of the numbers, okay, that you need. So this just gives us an idea, right, that in the near term, that, I mean, of course, we should work on these schemes that, once fault-tolerant, quantum computers become available, right, then we can hook up, for example, your favorite software, okay, so I think our software would hook up also to some quantum computers, okay, but they're not good enough right now to do PDE, so that's fine. Yeah, yes.
A small question on the CNOT.
Yes.
Does this solution assume that there is a fault-fault connectivity between the qubits?
Yeah, so here there are no assumptions, right, about if things are, less connected or others. This is kind of like the best case scenario. Well,
you can repeat the.
Oh, I'm sorry. I forget. So the question was, so these estimates of C-naughts, do we make any assumptions about all-to-all connectivity, right? So what that means is that, when people make these devices, say on 2D chips, I mean, depending on how they make them, sometimes geometrically it's just not possible, right, to connect, systems here with a system there. So it's difficult to do a C-naught between this system and that system, right? So then you have to, do more operations. And here, we don't make any assumptions, okay, about the geometry of these, so we can assume, any connectivity. So so in that sense, this is kind of like a good estimate. Like, this is the, Yes.
Yeah, second found it, what's in the lens trouble?
Sorry, epsilon? Oh yeah. So remember that we estimated the heat equation using the hyperbolic heat equation. So then this. Oh sorry. Repeat the question. Okay. So the question was what this epsilon is doing. Okay. Here. So with the heat equation example, you remember that we approximated the heat equation using the hyperbolic heat equation. And it's my fault because I never told you guys what epsilon is. I just forgot. In the hyperbolic heat equation, epsilon was a parameter that is like kind of tuning the viscosity, okay, of the system that you have. So, and it's also related to the time scale. So So with this kind of tuning, it just simply means that if this epsilon, is small enough, then we can actually, the hyperbolic heat equation can approximate the actual heat equation, right? Yes.
Another question regarding the Hamiltonian. When we use only CNOTs, that's tooling that the Hamiltonian has at most theater treatments, quadratic interaction terms, or if those CNOTs could represent like the Fourier gates and
Oh yeah. So the question was, this number of C-naughts actually mean the actual number of C-naughts, right? Or you just apply it, or they're kind of contained inside coupled gates and things like that.
Yes.
Yes.
And so is it necessary to interaction terms
Oh, so here, we it's a little bit different. So here, this is completely discretized, right? So what that means is that the structure that you have is kind of, a little bit lost, right? Like in this. So this is, and actually Shadi can tell you more, okay, about that, how to, simulate this explicitly, because what we do is that, they have a method of, when you're doing Hamiltonian simulation of each of the power of IHT, there's a particular block encoding scheme, right? So that's explicit, and this is, like according to that scheme. Yeah. Sorry, did I repeat the question for everybody? I forgot.
Sure.
Okay, sorry. Yeah. Okay, so Laura, how much time do we have? Sorry.
If you agree, can respond to 6 instead of 5, right? If it's okay for me.
Oh, it's okay. Is it okay for everybody else? Like, I don't know. Because
yes. Or mine just.
It's okay. I won't be offended. Like, we'll come back tomorrow as well.
Yes. I think all your question is many classes are coming at 15 moments.
Sorry, is that a... and then guys, if you need to leave, I won't be offended. Like, honestly, like, please. I know it's very hot in this room, so, yeah. All right, so boundary conditions, okay, and inhomogeneous PDEs. And these are just some examples. I have a reference list actually at the end, so I'll share all the slides as well with Laurent, so there will be references at the end. So I won't go into like a lot of details for everything, but just kind of as a note. So as an for example, how do we deal with artificial boundary conditions? Well, it turns out that so artificial boundary conditions are say you want to simulate Schrodinger's equation, but we don't have infinite space, okay, on our computer. So we do have to put, finite boundaries in. But the problem with putting finite boundaries in is that, because Schrodinger's equation is about waves, okay, and waves reflect, right? So then if you, for example, if you have, reflecting, boundary conditions, means that when your wave hits the boundary, it's going to reflect back. But the things that waves do is that, they interfere with each other, right? So it's going to then interfere with your solutions. So we should not have these reflecting boundaries. Instead, you should somehow have, the boundaries that absorb, right, the wave, so that it feels like you're actually going out into infinity, even though you're in finite space. And a way of dealing with that is actually the potential term, right, that you have. So they have a lot of different artificial boundary condition ones. So, one famous one is called like complex absorbing boundary condition. That's called CAP. There are other type of methods, like perfectly matched layers or Dirichlet to Neumann map. Okay. But one like CAP, for example, does this by saying, well, if we look at the kind of potential term, then this potential term actually has an imaginary part. Okay, so you can think about this as kind of the boundary, kind of the potential part having, the boundary is actually absorbing, right, part of the system. So now if it has a potential, if it has an imaginary part, then it's saying this is now not a unitary system anymore, right? But we know what to do if we have non-unitary systems. Okay, we Schrodingerize it. Okay, so that's one way of dealing with it. Okay, so that's one example. Okay, another example, we have physical boundary conditions. So like Dirichlet or Neumann, and also of course Robin boundary conditions. And what it does is that it turns discretized homogeneous PDEs into inhomogeneous PDEs. Okay, so as an example, right? So again, we have the heat equation example, right? We divide into grids, and suppose we use central difference schemes. Then for all the kernel points, meaning ones not at the boundaries, right? Then it behaves accordingly to how we think. Okay, but suppose we have boundaries, right? Say this is one dimensions. Okay, we have 0 in L. Then we know that u, okay, at 0t, that's equal to a, and u at L, okay, the other boundary condition at t is equal to b. Then we see that actually we the equation that we get for du1, right, where this is the first component, okay, of u, then we see we have this inhomogeneous term a, okay. So somehow inside, okay, everything else works the same, but at the boundaries, right, we're going to have inhomogeneous terms. So therefore, the whole system of PDEs, or actually now it's an ODE, right, because we've lost the spatial continuity, then it's going to have an inhomogeneous term. But then we see how we know how to deal with inhomogeneous terms, okay? Then we, dilate it, okay, as we did before, to make it homogeneous. Okay. Right, so, so I think I talked about this before, okay? This is just a reminder, right? How we deal with F, okay, an inhomogeneous term. Then, so we dilate the system. So now it's the original u times, 0 plus F tensor product 1. Okay, and then we end up with a homogeneous system. Okay, so I think I'm doing pretty good with time, okay, because I think I can even get to some of the part 2 things. So now near optimal, okay, strategies. So here we talked about Schrodingerisation, where it looked like the initial states were all kind of pretty easy, okay, to do, right? And we chose kind of the simplest one with the warp phase transformation because you might also remember that we can actually approximate the initial state with a Gaussian, okay, coherent state, which is kind of the state that directly comes out of, all the lasers. Okay. But what happens if we want to improve in things like precision? Okay, so nice. And this is maybe a little bit more important when you want to discretize your scheme. So then it doesn't really matter how messy your initial conditions are. Right? Because, if you have to discretize, you have to have universal devices anyway. Right? So, and this is just to say, it is possible, okay, to change, okay, the precision. So, but just a note on the original, okay, warp phase transformation. Okay, so the warp phase transformation still works, okay, because, this product, it works when size is above 0, okay. But however, and if we do have a backwards thing, then this is when psi is above psi star. Okay. But this in itself does not specify the conditions when psi is, below 0. Okay. So remember, like we were able to see that, in the case where, like the simplest kind of case, we do a symmetrization where we say, okay, if psi is, below 0, then we can say e is to the power of minus, okay, absolute value of psi. Then we get this symmetry. And this state can be approximated by a coherent state. Okay, it's very symmetrical. However, if you want to now do numerical methods on this, then we see that this exhibits first order convergence in psi because there's a lack of regularity, right, of each of the power minus psi. Because we have a sharp point at the front. Okay, so it doesn't this derivative is not well defined. Okay, at the sharp point. And since this is a regularity problem, then it means that when we do the Fourier transform, okay, because remember we have to do Fourier transforms and, inverse Fourier transforms, then the maximum value among the discrete Fourier modes, right, scales as 1 over epsilon, where 1 over epsilon is the precision, right, to which, you can discretize, right, your initial state, okay? So which means that, the schemes, they're accurate up to, right, 1 over epsilon. Like this is the precision. And the question is, can we improve that? Right. So, and again, of course, we can, right? Because the whole problem came from the fact that, this e to the power minus psi, it's got this sharp point, right? So the regularity is low. Okay, so all you need to do, right, because nothing needs to happen, right, when psi is above 0, right, because, everything there works. It's about what happens when psi is below 0. So all you have to do is kind of smooth over, like, this sharp, pointy bit. Okay, so once you smooth it over, like, the more smoothing that you have, right, so the higher the regularity, then, the better the precision that you can go. So I'll give some examples. So this is just to say, how much more precisely. So before the scaling goes as 1 over epsilon, and our question is, can we get to log 1 over epsilon, for example? How much regularity do we actually need for that? Well, so just here, an example. So we have a standard error, okay, between this sharp, okay, function e to the power minus psi. And if you want to use the approximation using its discrete Fourier transform, okay, then we see that it depends on your regularity R, okay? And remember, and psi is, within some boundary, okay, between, L and R, okay, your left and right boundaries. Now, if we impose, okay, this error to be, above, to be below epsilon, so this is the error, okay, to which we can approximate this, then the number of discretizations we need to have along the psi direction, so this is the extra dimension, so then this is now a function in terms of epsilon and in terms of the regularity. Now, if we want, right, to solve for, the scaling, right, to go as log, right, 1 on epsilon, okay, instead of just 1 on epsilon, then this means that our n has to be a function, okay, in terms of this with, log 1 over epsilon. And this means that R should scale like this in terms of 1 over epsilon. So we should find functions where to the right, where psi is above 0, it still scales as e to the power minus psi. But we want to smooth things over, right, on the left-hand side, right? So the regularity scales in this way with 1 over epsilon, okay? And therefore, in this way, the required regularity for psi gives, our eta max scaling as 1 over log 1 over epsilon. So these are some of the diagram, okay, for the kind of regularities we can have. So improving precisions. So the dotted line is the original one that we had, but we can see that, as we smooth things over, right, they kind of converge quite rapidly. Okay, so we just need, to have smoother functions like this. Yeah, but, so we can, it's possible to do. Now, experimentally, I don't like this so much, right, because it means that we do need to put a bit more effort in, kind of find states that, so because with this, when you have a Gaussian state, it's, symmetric and it's, very easy to approximate. But this one, you need to do a bit more, quantum control, like for your systems. And somehow we don't think it's worth doing because our precision is already all right. Okay, because here it's just, a factor of 1 over epsilon to log 1 over epsilon, which, for a lot of cases, it's, maybe not as important, okay, as some of the other scalings. So here it's a summary of comparison. So if you remember, so now if we're completely looking into the discretization scheme, then in principle, we can do things like, turn this into a linear algebra problem or directly use block encoding where we have like square roots of things, right? And squares. So now this is a comparison about, the queries, right, to A and the queries to the initial condition. And we see here with Schrodingerisation, so we do better than, the other ones. But I feel like, on this level, even though we do better, because, beta is always less than 1, even though we do better, like in terms of strict scaling, I think this is not the thing that we should concentrate on, actually. It's really, because what I said at the beginning, like we should focus a lot on the simplicity, right, of the algorithm that we're using. Right. And if things are very complicated, there are a lot of hidden factors in these big O's. Right. So if there are these extra things that you have to do, even though they don't contribute, right, it doesn't seem to contribute to these, larger kind of factors, but they will, right, in the long run, if you deal with real problems, contribute to the actual gate numbers. Right. And the actual number, because these are queries, remember. So, but this is a black box, right? This is a black box query. So how do you open that one up? Right, so all these questions actually matter, right? When it comes to you doing the programming, and if you're interested in actually going to a quantum industry and actually like Chardier, actually looking at the explicit gates and opening everything up, I mean, simplicity really matters. So it's not just looking at this bare level, right, of, oracle counts and things like that. But this is a comparison if you are interested. Okay, so, and I want to say a few things about foundational implications. Okay, so this is high-level philosophy now, like kind of a Friday evening kind of talk, part of the talk, yeah. I mean, I like thinking about these things, but I haven't made any progress. So if any of you guys want to, yes, chat about it. So this is something we do actually have a paper on, which is, putting Schrodingerisation in the context of, other dilation theories. Okay, so, so we can actually, so if you look at the Nagy unitary dilation theorem, like the proof for why that works, and this is, it looks complicated, but all it's saying is that you're able to embed a non-unitary system into a unitary system, okay? And Nagy shows that, like, the main proof for Nagy is really to use what the block encoding scheme is, right? So if something's non-unitary, then you dilate it by saying, okay, then you have, these off diagonals as like the square root of y minus a squared and, minus square root of y minus a squared and so on. So these things you've seen already. But however, now Schrodingerisation provides another proof, okay, of Nagy's dilation. And actually, then we can also extend to the infinite dimensional space as well, because Nagy is typically now with the finite matrix form. But here, we can do infinite. But now, so in saying that, what are all the possible classes of dilations and that are suitable for different problems? Okay, so this is kind of the big question because, I mean, we found one type of dilation, but, are there other kinds of dilations? Like, from a mathematical point of view, can we connect it to different, because I know that in math, dilation theory is like, it's huge, right? But when I speak to people who do dilation theory, I can't understand them because, it's very, very abstract. So it'll be very good to kind of, merge these two ideas because I have a feeling that really there's really a lot of deep math in, dilation theory that, can be made more understandable in such a way we can actually use them in algorithms. Because so far with a lot of these dilations, it's more, for foundational reasons. But I think this is more than foundations because we see that, these are useful things that we can actually use for our algorithms. So I feel like at the moment, these two feel like these areas are not, talking like as much, right? But I feel there's a lot to be learned, So if any of you guys, because I'm talking to mathematicians, right, are interested in, dilation theory and things like that, then we say actually, bring that over into the practical, realm, because it could actually be very useful. Okay, I just don't understand them right now. Well, I'm trying to talk to them, but it's very hard. Okay, so, and another interesting question is, well, what does this actually say about, simulability of, PDEs kind of more generally, right? So, for example, which PDEs do we know are classically efficiently simulable, which ones are not? Okay, and I think this question hasn't really, just hasn't been asked properly before, because we all kind of assume, if we have universal devices, we can simulate them, and we hear things about, maybe some of the condition numbers, or sparsity, things like that. But somehow, this is not as close to the actual physics of the PD, right? Because when we translate it into these kind of matrix languages, we're farther and farther removed from the physics of what's going on. Remember, because the physics of what's going on really lies, within things like the coefficients, the derivatives, and all these things have meaning, whether you're talking about transport or diffusion, right? Or how much, homogeneity you have in your system. So if we look at the qubit base, so say if we discretise everything, all right, already, then we know for qubit-based systems, there's something called the Gauss-Menil theorem. Now, I can't remember, has the Gauss-Menil theorem been covered in these lectures? No? Okay. So basically what, it's something that says that, you have a universal gate set, and, you have what are called Clifford gates, and you have, and of course, you have something called non-Clifford gates. And Clifford gates are somehow, you can think of them as easy to do, okay? And non-Cliffords are somehow hard, right? They're kind of the magical extra ingredient that kind of makes everything work. So if, that allows you to have universal, devices, but it's actually the hardest part, making the universal devices. So Gordon Mills there says, if you only have Clifford gates and projective measurements in the computational basis, then they can be, simulable, efficiently on a classical device. And it's really, having things like these public gates and so on that's actually making things more difficult. Now, if you now were to apply this to now our PDE, right, simulation, then once you discretize your PDE and you have this, huge matrix now that you have to decompose in terms of Clifford and non-Clifford gates, now I've like completely lost the physics, right? Like if you say, okay, how many non-Clifford gates do we actually need? Well, what does that actually mean, right, with respect to the original physics of the PDE that we're studying? So it kind of gets lost, right, in all of that, right? So hard to see, how non-Clifford gates are related to aspects of the PDE. So, but on the other hand, there's actually a version of the Gottesman-Neal theorem, but for continuous variable systems. And this is by, Butler, Sanders, Bronstein, and Emerger. And what they say is actually the, corresponding, statement is that they're classically easy states to do are Gaussian operations. And this is something we mentioned before. It's kind of the bread and butter of quantum optical, simulations, that they're kind of the equivalent of, Clifford gates. But the ones that are hard, right, for example, are non-Gaussian operations, and that they're kind of like the equivalent non-Clifford gates. And here with Schrodingerisation, like using the continuous variable, right, way of looking at these things, then we can actually see exactly, right, which part of the Hamiltonian requires Gaussianity, which parts do not. Okay, and these, because remember, x goes to x hat, derivative goes to IP hat, right? So you can go backward and match exactly like what are the hard parts of the Hamiltonian to what are the hard parts, right, of the original PDE. Okay, so at the moment, what is an open question is that so I told you Gaussian states are definitely easy, but I didn't tell you that all non-Gaussian states are hard. Okay, so at the moment, what is a foundational open question is which non-Gaussian states are actually not classically simulable, right, versus which ones actually are. Okay, so this is still an open question. So this is why it's a foundational question that once we know more about these things and how that maps onto the, to prove, right, the simulability of PDEs. Right, so yeah, so this is a foundational question. If, for people who don't just want to see the results, like actually, of the simulation, but you actually want to prove something more foundational. I mean, I think the continuous variable route actually gives, better guidance, right, to relate, the PDE, to relate the meaning, okay, of the PDE and the simulability. And even more philosophical thing, which is, and it's something that I mentioned at the beginning, right? So all the, classical, PDEs that we want to solve, they're, they derive from quantum mechanics. Okay, or at least in principle should be derived from quantum mechanics, if we believe in quantum mechanics at least. But it is the best tested theory of all times, more or less. So, right? So then we know, okay, in principle, quantum mechanics can reproduce all of that. But somehow here, with Schrodingerisation, it's kind of like taking a shortcut, right? It's saying that somehow all the information, right, that is contained, like, in the higher levels, okay, molecular dynamics, kinetic theory, continuum theory, and so on. If we look, again, if we look at linear cases, somehow all the information in there can be captured not in a super high dimensional quantum mechanical equation, which is the true quantum mechanical equation, right, underlying all those physics. But we only need to include, just increase it by a couple more dimensions. Okay, just one, like for homogeneous linear systems. Okay, so then it's really saying that once, with collective behavior, you actually lose a lot of information. Okay, but you can still be mapped onto some, foundational quantum mechanics. Okay, so what does that actually mean? And if indeed all of it can be, mapped onto quantum mechanics, right? So of course, quantum mechanics is quantum mechanics, but if higher levels, they can be mapped onto another quantum mechanics, then maybe it might be a route towards looking at the boundaries of these problems, right? Because you really look at the same equations, right? But in, slightly different dimensions, okay? So, but it's easy to work with different dimensions because all you need to do is to dilate it to a high space, right? And it's just a subspace, right, and the rest is zero, right? So this provides like a mathematical construct to which you can study the boundaries. Because before, you kind of had to do things like set h bar going to zero, things like that, right? But here, this is all quantum mechanics anyway. right? So does this provide a better mathematical tool to look at the emergence, right, of, classical from foundational quantum mechanical behavior? Yeah. So I have no idea, but I'm just putting it out there. This is Friday, so it's fine. Yeah. So a summary, right? So this is the summary. Okay. Well, this. Yeah. Yeah, and again, just kind of a reminder of the 4 different types of simulators we can have for PDEs. Classical digital or classical analog. And I do just want to emphasize again that regardless of the actual cost, right, of things. We see quantum analog. It's quantum cost is linear dimension, and we basically have 1 gate if we find the right Hamiltonian. And we don't need to discretise at all. But the thing is here, because we're actually exploiting entanglement, we actually see that, we can, simulate, we can keep things continuous, whereas classically we cannot. Because imagine, how do you classically in an analog way simulate, a 100-dimensional PDE, right? There are no 100 dimensions that we have, spatially around, okay? So how do we do that? So classically, people have to discretize PDEs into ODEs, right, and solve these systems in parallel. But then, you're losing the, full continuity. So, but with quantum case, because we have this tensor eta hat, this is actually entangling operation. So in that sense, we're also using something foundationally quantum to keep the continuity, right, across all the dimensions. And this is an example, just, these are all in the papers, but it's just say all the equations, and we have, the order of terms in the Hamiltonian and the number of terms we have in terms of dimension, and, the power, the highest power of the derivatives. So, and the cost for discretized schemes, this is something that we mentioned before. And then this is a list of what I consider at least to be the benefits, apart from kind of the simplicity. We can take advantage of both, continuous simulation, no discretization of PDEs are needed. But however, you could discretize if you wanted to, because again, eventually, I think if we want to have good control of the errors, at the moment, it's about whether or not we can do it or not. Qubit case, we can't do it right now. Okay, no one can with any of their methods, but at least here we can. But in going on from that, right, if we want more, better and better and better, then, qubits, because we can control the errors better, if, we have fault tolerance and so on, then we can still do this. So the formalism can be easily adapted either to the discrete or continuous setting or actually hybrid, okay, version of both. Because, and also if you, it avoids complications of, matrix inversion type methods. So something that's Anishka discussed yesterday, I think. And you will see dependence on things like, condition numbers and so on, which we don't have here. And, I mentioned before, we can see explicitly which parts of the PDE, right, requires entangling operations and, which parts requires non-Gaussianity, and so on. And the cost here, is in D instead of exponential in D, if you compare it to, finite difference methods and these type of methods. So everything we've covered is, within the context of a larger program of things, of thinking about dilation. So here it is saying if we have linear homogeneous PDEs, we just add 1 dimension to make it Schrodinger. Okay, so this is one type of dilation. Now tomorrow I'll talk about what happens when we have nonlinear problems, right? Then it turns out that for some classes of, PDEs, we can also perform a dilation to make them linear PDEs, right? And then we can use Schrodingerisation. Okay, but so, how do we dimension lift, right? So that nonlinear becomes linear. Things that we might not have time to talk about, but I'll just mention these here. So if we have uncertain problems, then we have, dilations where, say if we have L uncertain variables, then we just need to add in L extra dimensions, and then the uncertain problem becomes a deterministic problem. Okay, and then we automatically get an ensemble average that way. And 4, which I like very much, but I guess none of you guys work on this. But in case you're interested, so if you have linear non-autonomous systems, then we just need to add a maximum of 2 dimensions for them to become linear autonomous systems. Okay, and we actually see this as a unifying construction in which, this is fully continuous, okay, dilation. But if you discretize in different ways, we can see that it actually reproduces most of the known quantum algorithms for simulating time-dependent Hamiltonian problems. Okay, so the message that, if we do these dilations classically, because you're like, okay, we can also, do these dilations classically. But the point is, of course, if you do these classically, even adding 1 or 2 dimensions, that's going to cost you, right, a lot, right? But it's classically costly because in quantum, we don't care about extra dimensions so much. That's why we can have the benefit of the dilations without also incurring the extra cost of curse-of-dimensionality. So this is kind of the, the philosophy, okay, of the different algorithms that we have. Like typically, like in classical algorithms, you think about when you have high dimensional problems, you do dimensional reduction type of methods, okay? But usually, when you do this dimensional kind of reduction, you end up with a lot of other problems, right? You have to truncate things, right? And linear problems actually become nonlinear, okay? And things like that. But here, what we do is that we go the other way around, so that, when we have a low dimensional problem or like a high dimensional problem, we increase it, but not too high, not too much higher, which then we see like some certain complications like uncertainty, being non-autonomous and nonlinear, that become linear, certain, and autonomous. Okay, and Schrodingerisation is also kind of part of that. And it'll be great, right, if you guys can help to add to this list. Yeah, so other kinds of dilations in terms of the problems that you see. Okay, so because I think this is a general philosophy when we're thinking about quantum algorithms for quantum devices, because quantum devices, they're just linear, right? So there's nothing you can do about that, right? At least fundamental quantum mechanics. So, but the good thing is that, they can help you resolve your curse-of-dimensionality. So any kind of mappings, that can map things to linear things, deterministic things, if you, look at deterministic, quantum computers, which is a lot of we have. So then all these type of dilations would help for that. Okay, so it's not just Schrodingerisation, but actually a whole class of, things that can be done. So this is the reference list for part 1. So these are the kind of basic. So the first 2 papers are, just I guess the first 2 papers. But the last 2 are, are the one where, we change the initial ancilla condition, to increase the precision. And the last one is, putting Schrodingerisation in the context of the Nagy dilation theorem. So, and, if you're interested in particularly for analog and the way, it's related to Jaynes-Cummings type models, we have references on that. And these are the ill-posed and inhomogeneous papers. So these boundary conditions papers, so, and these are the part 2 topics. So, and I guess you guys voted for nonlinear and linear algebra. Okay, thank you.
It's a thought. Thank you very much. So are there any questions?
I have a question about the heat equation you mentioned and the derivation with a linear system. And I'm a bit curious about the value of epsilon you considered within this approximation. So the numerical results are interesting, but what about what happens if you let epsilon vary? I mean, epsilon is quite small.
So the question is, I'll repeat answers. Oh, it's okay. Okay, good. But I also like to be just when I don't understand the question. So remember here, like you're choosing like epsilon to make your life as easy as possible, right? Because if the point is to actually simulate the heat equation. So here I didn't actually read this out very well. So you see, like if we want, so what this lemma says is that if you want to approximate U tilde, that's the original heat equation, right, with U, which is solution of the system. And if this is above like order epsilon squared, then this is true, right, when your time, right, is above order epsilon squared, right? So if you choose your epsilon to be large, that's fine, right? But then you just need your time, like the time that you simulate this system to go on for longer. Yeah, so you can vary that as you like, but the point is that it's really a scale relative to the time of the total simulation. Yeah.
Thank you.
Yes, I had a question about when you speak about precision. So you said that you wanted to smooth out basically the cusp of the exponential minus.
Yeah.
But could you also approximate the exponential by a sum of Gaussians and then kind of sum up results, or is it?
You mean this one, right?
Yeah. So here you could also approximate the exponential minus x by a sum of Gaussians.
You want to approximate the exponential with the sum of Gaussian. Well, I mean, the thing to make sure is that on this side, right, from 0 onwards, this has to be the green line.
So you want to, but you said that in the experiment, anyway, you would use a Gaussian packet. So
so experimentally, yes. So I didn't actually show the numerical results for that on, what the, so in, this is actually mostly just for discretise things to show it's possible, okay? But here, if we have a Gaussian, it's possible to do. Oh, sorry, your question is, instead of using one Gaussian, you use a sum of Gaussians?
Yes.
To do, but so a sum of Gaussians is unfortunately not a Gaussian, so which means that it's hard, right? If you want to do it on an optical system. So the way that we're doing this experimentally is that the initial state that's coming in, this is kind of, you can think of, it's like an optical state, right? So, and with optical states, these just Gaussian states are good, but some of the Gaussians not good. Yeah, it's not easy to do.
So maybe we should discuss a bit.
So it's like what I was saying, if you want to do this in a continuous variable way, you have to think a little bit harder about the quantum control problem that allows you to go beyond the non-Gaussianity.
Okay, maybe we have time for one more question if necessary. Okay. Yes.
Yes.
My question is about the hyperbolization. So for the hyperbolization in general, if you run it in a classical computer, you might notice some reduction in the computational time. But my question is, if you run the hyperbolization of heat equation, say, in quantum computers, and then you run the same heat equation without making any hyperbolization to it, do you find any advantages in the computational?
So here the whole point of this one is because we notice, so if you want to do Schrodingerisation directly on the heat equation, we notice that the Hamiltonian, it goes like, p hat squared, tensor eta hat. And I went to my friend who does superconducting, he's like, oh yeah, he's like, yeah, we have it, right? So then, but then when you can ask Yoe more about that, but we spent a long time, because he immediately saw it, and it's like, we have it. But then to actually control the parameters, because the Hamiltonian doesn't, the real Hamiltonian that has this phi squared tensor eta hat, but he also has some other terms that we want to tune, so we suppress it, right? Because we don't want them to be there. It was actually quite hard for them. I mean, it is possible, but, we wanted to do this as quickly as possible. So then, so it was more difficult to tune. And then while, they were working on that, then we thought, okay, well, let's try a different route, right? And so that's how it came about. So this one is, if we, Schrodingerize this one, then it becomes this James Cummings-like thing. And then, then my friend was like, oh, that's even easier. So we just went directly to that. So that's the point of that. But I don't know of, numerical advantages like with this, because it's, it's not actually the heat equation. However, I think these hyperbolic are interesting in their own right, actually. So we're actually exploring kind of that route. Like, maybe if you have, if you work on this, have some input on that, it'll be really great. Yeah, I don't know enough about this. Thanks. Next.
Okay, so thank you very much, Nana. And so maybe we can thank her again.
Oh, let's do this. And
so maybe I forgot. Is there any online question? No? Okay, so thank you, everyone. I'm afraid there won't be any Zoom for tomorrow on Saturday, because there is no broadcast for the courses tomorrow. So I say bye-bye to the online audience. And we're lucky. We'll work tomorrow with Nana and other lectures. Thank you very much to everyone.
Thanks for staying in the heat.
Yes.
Doing the heat equation, so it's so pretty.